It began as a solution. In the early 20th century, agriculture faced a growing challenge. As populations increased, the demand for food rose with it. Farmers needed ways to protect crops from insects, pests, and disease. Without protection, entire harvests could be lost. Science stepped in to help. Chemists began developing synthetic compounds that could control pests more effectively than traditional methods. Among these innovations were early chemical pesticides and compounds that would later evolve into substances like dichlorodiphenyl and chlorofluorocarbons. At first, these discoveries were seen as breakthroughs. Crops became easier to protect. Food production increased. Farmers gained a powerful tool that helped stabilize supply and reduce losses. In a world where food security was uncertain, this change mattered. But the story did not end in the fields. Some of these chemical compounds had properties that made them incredibly stable. They did not break down easily. They could persist in the environment long after their use. That stability, once seen as an advantage, became a problem. Over time, scientists began to observe unexpected effects. These substances were not staying where they were applied. They moved through air, water, and ecosystems. They accumulated in living organisms. They traveled far beyond the farms where they were first used. Among the most critical discoveries was the impact on the Earth's upper atmosphere. Compounds like chlorofluorocarbons, widely used in refrigeration, aerosols, and industrial processes, were rising into the stratosphere. There, they interacted with ozone, a layer of gas that protects life on Earth by absorbing harmful ultraviolet radiation from the sun. The reaction was not immediate. It was gradual, almost invisible, but it was persistent. Molecules released at ground level were reaching the upper atmosphere and breaking down ozone over time. As the ozone layer weakened, more ultraviolet radiation began to reach the Earth's surface. This had serious implications. Increased radiation affects human health, raising the risk of skin damage and other conditions. It impacts ecosystems, particularly crops and marine life that are sensitive to environmental changes. The system that once helped agriculture was now affecting the planet itself. What made this situation more complex was that the damage was not caused by a single action. It was the result of widespread use across industries and countries over many years. No single field or nation controlled the outcome. It was a global system, and it required a global response. Scientists raised concerns. Research expanded. Evidence became clearer. Eventually, nations came together to address the problem through international agreements like the Montreal Protocol, which aimed to reduce and eventually eliminate the use of ozone-depleting substances. It was one of the most coordinated environmental responses in history, and it showed something important. Human innovation can solve immediate problems, but it can also create long-term consequences that are not visible at the start. The same knowledge that increased food production also revealed the limits of acting without full understanding of system-wide effects. Today, the ozone layer is slowly recovering, but the lesson remains. Progress is not only about solving problems, it is about understanding the systems those solutions enter. Why do we learn history every day? Because moments like this show that solutions must be tested, not only for effectiveness, but for long-term impact, helping the present generation build smarter, more responsible innovations, and guiding future generations to protect the balance between progress and the planet. History is not old. History is living inside us. One day, one event, one lesson. Mr. Feedy,